Hello and welcome to this training session where we'll be talking about today using the iStar sCMOS camera as the master to drive your experimental setup. So last time we talked we gave a bit of an overview of the camera. I just want to reiterate that now because this will be quite critical when understanding the timings and features we're going to be discussing today. So as you'll recall, the iStar sCMOS camera is broken up into several components at the front end. We have the input window upon which the photocathode substrate is laid. We then have behind this the photocathode, which critically converts photons into photoelectrons and is what we use for gating. So when we talk about timing diagrams later on, we'll be talking about gating the photocathode. And then behind that we have the microchannel plate, which applies the gain to our image, or scales up our photoelectrons and applies gain to our image. Behind that we then have our phosphor, which then converts the photoelectrons into visible photons, which are detectable by the sensor. And then between that, we have the sensor's intensifier coupling interface, where we then channel our photons onto our sensor. And then behind that, we have a 2D, CCD, or sCMOS sensor. In our video today, we'll be using an iStar sCMOS camera. So at the back of our iStar sCMOS camera, we have several various connections. And I'll show you what we have connected in our setup in a moment. But just to run through them, first and foremost, we have the on-off power switch. We have an IC2C connector. This is used primarily if you want to drive a shutter from the camera, independent of your spectrometer for whatever reason. We then here have an ARM monitor, and this is particularly important when you're using the camera as a slave, because this is the output for which your camera will send a signal to let you know it is ready to accept an incoming trigger to start the sensor acquisition again. We also have a direct gate input, and this can be used for directly triggering the intensifier and bypassing the internal DDG. This can maybe be used if you're trying to really minimize your jitter when you're using some kind of external triggering setup. We also have a variety of outputs, so output A, B, and C. These are used as triggers, so when you're using the camera either as a master or as a secondary trigger. These are outputs that can be sent from the camera to up to 3 different sources. So it could be if you're triggering a laser to fire, for instance, from the camera, or it could just be to move a sample stage or something like that. We also have the USB interface here at the back, and we have the power supply 12 volts 9 amp maximum input. And we also have at the back these coolant connectors, which you use if you're planning to water cool the camera to obtain better thermal stability. We also have a fire pulse output, which gives you detailed information if you have your camera hooked up to, say, an oscilloscope, which enables you to look at where the exposure time of the sensor lies in relation to all the other timing measurements you have going on. So, for instance, as you'll see later on the oscilloscope, you can see when your sensor is active and when it is inactive, and then you can use this to then line up where, for example, your gate falls or your external output and triggers go to your laser, etc., to then line everything up. And then lastly, we have our external trigger input. This is particularly important if you've got the camera as a slave and you're using an external source, such as a trigger or a DDG, to then trigger the camera. So here we just have a diagram of what our setup is going to be today, where we have the camera as a master. So we have our iStar sCMOS camera, and we've got it connected to a laptop through the USB, and we're going to use this connection to set our software settings and then use the software as the trigger for our setup. We then have a cable going from the gate monitor on the side of the camera to an oscilloscope, and so from this cable we will be able to see the time intervals of the gating of the camera. And then also out the back of the camera we have the fire out signal to signify exactly when our sensor is active and inactive relative to our gate monitor. And we also, for illustrative purposes, have another output A out of the camera. We've used it also. We thought we might include this as this just illustrates that you might be using this to trigger a laser or some such thing. So yeah, in terms of the ports, we're using the fire, the output A, the USB connection, and of course we have it plugged in using the power. Here we have our iStar sCMOS camera that we're going to be using for the purpose of this demo. As you can see at the front, we have our photocathode window. Currently we have no lens on it, but for the purposes of this demo, we'll be using a C-mount flange and a C-mount lens, which we just screw in like this. Now it's worth noting on the iStar sCMOS that we have two fans, one above and below the side of the camera. It's important that you keep these clear of obstruction when you're using the camera, because otherwise that can impede the heating of the camera. Here we have our gate monitor, which we'll connect a cable to link to our oscilloscope in a moment. And down here we have a dry gas channel to help remove heat from the photocathode. And so you can blow cold air through this, and this helps to minimize your EBI thermal noise. And this can be particularly useful if you're doing some kind of photon counting application. So one thing to bear in mind if you're using an iStar sCMOS camera is you may want to use it for water cooling. So here at the back of the camera we have the water taps. One consideration you should take into account is, depending on the temperature of your water and the humidity of your room, the actual dew point could be an issue, because you don't want condensation forming on the inside of your camera, because that would be quite catastrophic. So what you can do is, if you look on our hardware guide for the iStar sCMOS, you'll see this graph which shows you the various humidities at which you could expect condensation to form on your camera. So it's very important that, depending on the ambient temperature and humidity you're working at, that you take into account this consideration. And so if you are using water cooling, just make sure that you stay above the dew point so you're not getting any condensation inside your camera. So as you can see here, we have now set up our iStar sCMOS camera and connected it to our oscilloscope. You can see here the cables marked in blue are our fire pulse cables. These provide a reference signal to the display and a representation of when the sensor starts acquiring and finishes acquiring. It doesn't include readout time, but it is a mirror of exposure time. One thing that's quite important to mention is it's important with these cables to match the impedance of the system, such that you don't get any distortion or reflections in your oscilloscope trace, which can distort basically the waveform and make it harder to see exactly when your timings are falling, etc. And secondly, you can see in orange we've attached to the front of our iStar sCMOS a cable into the gate monitor. This effectively allows us to directly monitor the gating of the photocathode. This is typically hidden behind a grommet on the camera. So this is actually an AC coupled setup, and what effectively is happening within your intensifier is there's a wire wrapped around the photocathode, and this is able to pick up pulses from the gate, and this gives us then some temporal information about where the gating is occurring, and we can then look at this in relation to our fire pulse and other outputs in the oscilloscope. And thirdly, we have in yellow, we've got our camera hooked up to output A, and so this is a signal that, as mentioned before, you could use to trigger some kind of third-party laser or instrument or stage, depending on what experiment you're doing. And we've put that on here for demonstrative purposes. So we've set our oscilloscope to trigger off fire pulse 1. That's our channel 1, our blue wire going into the oscilloscope. The impedances of all our cables are set to 50 ohms. Apart from channel 2, which is our gate monitor, this is actually set to AC high impedance, and we'll see in a minute when we show this that we're just seeing the edges of the gate, not the whole gate, when we actually show it on the oscilloscope. So now I've just gone into our Andor Solar software, and I'm going to talk you through just briefly how we're going to set up for our first image acquisition, which will just be taking a single image and then giving a bit of a view of what that looks like on our oscilloscope with our current setup. So our camera is already turned on and it's cooled down to 0 degrees. We're going to run it in single scan acquisition mode. We'll have an exposure time of 0.01 seconds, and or 10 milliseconds, and we're going to set the camera to gate with a width of 1 millisecond, and we're going to set output A with a 1 millisecond delay with a width of 1 millisecond, just to illustrate where that will fall on the oscilloscope and in a timing diagram. We've got the binning set to 1x1 binning. Could be 2x2, but we've got lots of light where we are, so that's perfectly fine. And yes, the reason we chose millisecond gating was just to make our lives a bit easier and make it more easy to visualize in the oscilloscope. So now we've set our parameters here in Solace, we're going to just press our acquire button, and as you can see, this very fine logo in front of us. But let's take a look at what this actually means for our oscilloscope. And one of the best ways of doing this is if we put it in live view mode, so we're taking repeated images, we can then bring up our oscilloscope trace, which you can see here. And just for clarity's sake, we've also opened this in our connects our oscilloscope through our web address to our browser, so we can actually see our oscilloscope in some clarity. So if I just refresh this, so yeah, I've just loaded our oscilloscope trace here, and as you can see, we've got our top pulse labeled 1, which this is our fire output pulse. So this is our sensor starting in the exposure, and everything else is then timed according to this. You can see this rise and fall on the timescale. And so here we've got, and number 2, we have our gate pulse, and because it's an AC current, at some points it's negative at one edge and positive at the other edge. And then in number 3 in pink here, we have our output pulse, just timed as we'd set it to 1 millisecond. So each of these boxes is 2 milliseconds, so you can see a 1 millisecond, it's a half box, and it's 1 millisecond delayed as you'd expect. So, and what we could do now is, just to illustrate the point, we can show what happens when, say, we change our gate width, or we change our delay time. So let's just do that. So that's the first trace we've got. Just for illustrative purposes, if we say we increased our gate width to say 5 milliseconds, stop our acquisition, increase this to 5 milliseconds, and we start acquiring again. You can see instantly in the oscilloscope a significant increase in the gate width. So this is what it was before. We update it now, and you can see it's increased greatly in width. Bear in mind that with the gate oscilloscope trace, the rising edge denotes the start, and the rising edge denotes the end. Less so the tailing off. So if now, just to illustrate, if we say change our the delay on our gate, so go back here, stop our acquisition, and we can change our delay to say 2 milliseconds, and we can do this on output A, we can make it say 5 milliseconds if we wanted to. And just I think it's worth just demonstrating this, so to show what difference this makes in the oscilloscope, so and the sort of timing of the whole sequence. So say we go back into real time now, and we go back to our oscilloscope and have a look at how it's changed now that we've increased the delay between our gate starting and our output starting. You can see here that our gate has moved along now and is more central now into terms of our sensor exposure, and our output A signal has now also moved in conjunction with the time delay that we'd added to it. This is just to directly observe what happens when you do change these timing parameters, and how you can mess around in the software to then tweak your experimental timings, maybe with the help of an oscilloscope, to figure out the optimal parameters for your particular experimental setup. Okay, now I want to just talk briefly about background correction mode, as I think it's a good way to easily improve your signal to noise ratio, make your image look better, and is relatively straightforward and easy to do. So if we take an image, before we do any background correction or anything, just for comparison's sake, and I'll just save that somewhere. One. There, it's open. And now what we can do is we can take a background image, take background. We're going to do it with the photocathode off, though depending on what you're trying to do or what background you're trying to eliminate, you might have to do it with on. It's very specific. And we have our background image. And now if we take now what we can do is go to Acquisition, Data Type Setup, and here we can change our data type from counts to counts background corrected. So this means any image we take will then have that background subtracted out. And now we can take an image, and this is now a background corrected image. And it can be hard to tell, but there is perhaps a minor increase in the quality and clarity of the image. It's slightly less distorted than the one on the left. So it's, unless you really zoom in and get have a real close look, it can be quite difficult to tell. So one thing you can notice if you actually you click on your image that is background corrected, if you click around, say here in the dark region, you'll see that the count number is still relatively high, like 107 or so. But if we look on our background corrected image, we're pretty much at 0 counts for all intents and purposes, and hence we can see that we've increased the quality of our image. So now for our next example, I want to talk about using the camera to acquire kinetic series with the camera as the master. So it's very similar to how we had it set up last time, but imagine we have, we're going to generate multiple events in time triggered by the camera. For instance, 2 events as shown here. When the camera as the master is triggered, it'll start the sensor exposure, and we'll set the sensor exposure time such that it will be long enough to encompass whatever time we set this event to occur. So part of this will be, we've got our output signal, in the case of our setup output A, where we will trigger some kind of external output, which then means our event occurs in time where we want it to, in relation to the sensor exposure time and to the photocathode gate. So we can shift the photocathode gate in time to help calibrate the link between our output and the event that's occurring. And we'll then do this when you set the camera as the master in a kinetic series. If you say want to acquire 10 frames in a kinetic series, it will then automatically trigger 10 sequences of this event and give you 10 frames. Hence you'll have just repeating blocks following afterwards once the camera is ready, has read out, and then has waited a sufficient amount of time, depending on what you set it to. So if we were going to set a kinetic series up in solid software, we would go to the acquisition mode and swap to kinetic series. I think we'll keep the exposure time about the same, but we can change our kinetic series length. I say we do a kinetic series of 10, say. And just so our widths are quite visible, perhaps, on the oscilloscope, I think if we set this to, say, 3 milliseconds in terms of our gate width, and 7 milliseconds in terms of output A, and this should hopefully give us a good kinetic series. So now if we go to acquire, I think we'll go for real time just so we can see it quite clearly on the oscilloscope. And if we zoom our oscilloscope out a little bit, you can actually see the repeating series of the kinetic series as it displays if you have multiple acquisitions. So this is what the oscilloscope looks like directly with the camera. So if we just pause it so it's a single sequence on the oscilloscope, this maybe makes it a bit easier for us to capture a single frame. You can see here we have a kinetic series of 3 frames. I mean, can we capture these within the sort of field of view of the oscilloscope? Obviously, there would be 7 more if we went for 10 frame kinetic series. And within each of these frames, we have our fire signal here at the top, showing when our sensor is active. We've got our gate opening and closing signal, and we also have our output A signal as well, which could be sooner or later depending on what you're trying to trigger, etc. So next I want to just talk briefly about gate step mode, because this is a particularly useful feature available on all our iStar products. And this is a particularly useful thing because if you're looking at some kind of phenomena that has some kind of time evolution, but is a recurring phenomena, so it's the same every time you say pulse a laser at a target and generate a plasma, and the plasma looks the same every single time you do it, Gate step mode is a great tool to then having a sequence of events captured in time. So for instance, if you're looking at a plasma plume, you can set your camera to take 100 frames, and on each frame it's going to gate at a slightly later time frame, and then you can build up a picture such as this, for instance, to capture that change in time. So if we take a look at what kind of timing diagram we might expect in gate step mode, and conversely how this might then look when we then look at it in real life on an oscilloscope. So in gate step mode, what we have is we have because the camera's a mass, we have our internal trigger which sets everything in motion, and we can use this internal trigger to trigger the sensor, but also to trigger an output. So output A in our particular example instance, and this output A is then used to then trigger an event in time, which then has a sort of maybe a decay profile or some kind of temporal element that we want to capture with multiple photocathode gate slices moving through time. So in our first image in gate step mode, we'll have our photocathode at a set distance, delta 1. And what you can do in gate step mode is you can configure it so delta 1 then changes by a certain increment per additional image. So in our second gate step mode image, what we would see is delta 1 become delta 2 with a larger time interval between that and the first one. So we would capture a different spatial element of whatever phenomena we're looking at. And then this is true obviously for later ones where we even have it, extend that time further. And you can then set this to then capture every element of the phenomena that you want to look at and spatially resolve it and image it in time. Right, to set up a gate step in software, you need to be in kinetic series mode, set a series length of whatever you plan to set it to. So in this case, we're going to go with 5. We've changed our gate width to 10 milliseconds, and our exposure time is 0.1 seconds. And so you need to tick this box here, which is step. And here in this DDD step box, you need to set what you want your constant change in gate width to be. So we're going to go 10 milliseconds in this instance. And that's pretty much it. So from here now we can just press acquire. And if we take a look at our oscilloscope, you'll see that the, one second. Yeah. If we take a look at the oscilloscope trace from this, what you'll see is that the gate pulse is increasing by 10 milliseconds time-wise relative to the sensor exposure. So we're progressing through time with each sequential pulse. And from this, we could build up as we discussed before, our time-resolved observations of certain phenomena, luminescence, etc., or plasmas, whatever we're looking at, and we can build that up in time. So the next mode of operation for the iStar sCMOS, when the camera is being used as the master, that I want to talk about is integrate on chip. And integrate on chip is very useful when you have an event such as this, where you have the same recurring event happening over and over again, but perhaps your signal is relatively weak and you want to get a good signal to noise ratio. And instead of stacking multiple frames on top of each other where you have to read out each frame every time, what you can do is you can take one frame and stack multiple events on top of each other in the single frame to get the best signal to noise ratio. So if you have an event like this where you have an output A, for instance, that's triggering your event, and you that can set the event starting as before, but what you do is you have your sensor on a long exposure time, so your sensor is exposing across multiple events. So here we have 3 events within the span of this single sensor exposure. And what you can do is you can gate your photocathode using integrate on chip in the software, so that you're in the same time domain, so you're capturing images at exactly the same time, so at the same part of this event or whatever it is you're looking at, but you're opening the gate for the same part of the event in the same exposure. So all that, you're just building intensity through every event, and you can do this, multiple times depending on what you're trying to do, and it's an excellent way of getting better signal to noise. So setup integrate on chip, it's relatively straightforward. In your gating settings here, you can go to integrate on chip and tick the box. And then what you can do here is you can then set the number of pulses you want to see within your particular exposure time. And this is then limited by the sort of length of exposure and the sort of maximum and the gate width that you've set. So in this instance, the maximum we can have is 5. So let's have 5 for this demonstration purposes. And then simply we just press acquire. And if we take a look at our oscilloscope trace, and here on our oscilloscope trace, you can see that we're opening the gate 5 times during each sensor exposure, building up more signals, reducing our signal to noise, building up more intensity and across the sensor, but within the same exposure, so we get more intensity but less read noise per count.
Thank you for watching the Andor iStar sCMOS demo videos.